Hello, and welcome to this presentation on enhancing rail operational performance through rapidly deployed analytics. My name is Andrew Smith from the UK, and I am a senior product manager here at Bentley Systems. My passion is for turning rail measurement data into measurable value for rail stakeholders. Today, I'll be looking at a new software configuration from Bentley Systems and how it can help rail owner operators maximize the value from existing linear data sets. Note that tools are only part of the solution here, and that hearts and minds of the engineers and process change are even more critical. Tools can only support the workforce in delivering change. So my agenda for today, after a brief introduction, I'll look at the challenges and opportunities associated with linear asset management and linear decision support. Then I'll level set some terminology that we'll be using before looking at the new solution from Bentley, which is AssetWise Rail Condition Analytics, and then conclusions before we head into a Q&A session. So to start with, just one slide background on Bentley, for those who don't know us. Bentley has been a leader in software for rail for well over 30 years, supporting civil infrastructure work on the world's busiest, oldest, largest rail systems throughout the asset lifecycle. We're used from requirements management and conceptual design through detailed design, construction, maintenance and change management. So spanning the entire asset lifecycle for all the civil infrastructure. So let's have a quick look at some of the challenges associated with track maintenance. We all understand that maintaining a safe, reliable, efficient, well-perceived network is the primary objective of a rail owner operator. Note the scope of my presentation is focused purely on the linear asset, notably the rails and the associated track geometry. In general, the industry is moving towards a condition-based maintenance methodology, including using specialist linear decision support solutions to manage specialist datasets such as track geometry. This has the advantage that decisions on maintenance and renewal priorities can be based on objective measures, but does mean that any decisions made are only as good as the data available. This provides challenges of data quality and data accessibility, and a requirement for both management and engineers to embrace and move towards a data-driven strategy, as mentioned previously by multiple panelists. Historically, moving to a condition-based linear decision support solution has been an expensive and time-consuming process, requiring changes to both process and technology, which could be prohibitive for all but the largest rail operators. However, the same issues and constraints apply to the full spectrum of rail networks. So a solution to meet these challenges needs to match a number of key capabilities. It needs to allow users to intuitively see and understand the current state of the assets derived from all available data and seen in the context of related assets and historic works and condition scores. It needs to be kept continuously up to date with the latest measurements, usage information, and asset changes. And it needs to be able to support maintenance and renewal decisions based on asset condition, context, expected life, and observed deterioration rates. Critically, the solution also needs to be able to be deployed rapidly and at low cost in order to start delivering return on investment sooner. So the bad news for our assets, our track assets in particular, is that they tend to deteriorate over time. The better news for us is much of that deterioration tends to happen in quite a predictable fashion. So ride quality, rail wear, and so on can be measured objectively, and deterioration plotted to point of failure or point of functional failure. Functional failure can also be classified objectively, e.g. as a threshold for a quality index. Our focus is to ensure that the system can be maintained sustainably to a compliant standard for a known level of effort and resource, avoiding functional failures such as speed restrictions, and certainly avoiding full failure of any key assets. McKinsey performed a review of the rail sector recently and determined that savings of 10 to 15% of the total maintenance budget were possible by moving to a condition-based maintenance process and regime, and a further 5 to 10% by moving from there to a proactive maintenance regime. It's important to note that these savings are possible by changing the maintenance and renewal processes to consider the asset condition and rate of change of asset condition. Linear decision support is simply a tool that can support this process change. But on the other hand, the savings that we're talking about here are huge. So the potential upside is enormous for going down this route of condition-based maintenance and proactive maintenance. Before we drill into data analysis and visualization, let's take a moment to clarify and level set a few key terms that we'll be using throughout the rest of the presentation. Firstly, linear asset management. Asset management is the systematic approach to governance and realization of value from assets. Linear asset management is a subdiscipline of this that focuses solely on the linear assets, the rail, the ballast, the ties or sleepers, elements of electrification, and so on. At its heart are a series of documented processes for use, assessment, and maintenance of the asset, all designed to keep the system working as required in a sustainable fashion. Linear decision support tools are tools that can be used by engineers when they are selecting where, when, and what work to undertake to sustain their linear rail system. They typically work by bringing together data from multiple sources, often from distinct systems or data silos. These data sets can then be analyzed and visualized by engineers to provide supporting information to help them make better decisions and to apply the processes required for linear asset management. Track geometry measurements next. Track geometry measurements are performed by track geometry recording vehicles, either dedicated vehicles or sensors fitted on in-service vehicles, which is actually becoming a more prevalent approach nowadays. These vehicles traverse the network, making measurements every 20 centimeters or so, typically. The measurements give an indication of the condition of the track and its suitability to deliver the timetable. The measurements can also be analyzed to look for changes over time to support the maintenance and renewal decision-making process. Rail wear. Rail wear is derived from rail profile measurements, typically performed by laser scanners on the head of the rail, perpendicular to the head of the rail. These are then cross-referenced against the equivalent unworn rail profile to generate levels of rail head wear and side wear, as well as several other parameters. These parameters can then be used to assess the remaining life of the rails by measuring the rate of wear between successive runs and cross-referencing that to the tonnage and to the radius of curves and cant deficiency in particular. Now we come on to the basic forms of analysis of measurement data. One of these uses all of the data to give scores over the entire asset, which is our track quality index, and the other focuses on areas where there are discrete issues. First, we'll look at the overall condition scores. In rail, these are often called track quality indexes. Each track quality index is designed to give a score to a particular aspect of the track, for example, the overall wear on the rails or the condition of the ballast. The rail network is often segmented or chopped up into lengths over which these scores are reported. When this happens, it's vital to ensure that the segments are appropriate to the score that is being produced. So the segmentation we use for geometry is completely different to the segmentation you may choose to use for rail wear. The source data for the track quality index is then processed against each segment in turn, and a score is produced for the segment from one or more channels of measurement data, maybe cross-referencing to other data sets. These scores represent the state of an asset on the day the measurement took place, and they can then be analyzed over time to determine the rate at which the asset is changing or deteriorating. They can also be used to see the effectiveness of historic maintenance that's taken place by looking at the improvement or the difference in the rate of change of condition between before and after the maintenance work. Thresholds are often applied to track quality indexes, triggering maintenance activities, renewals, or speed restrictions. The same data used to determine the overall track quality is also used to identify localized areas where maintenance needs to be applied. Typically, each channel of recorded data from a measurement will have several sets of thresholds applied to it to represent different levels of severity for issues. So maintenance issues, safety issues, potentially your shut the line faults. These thresholds typically vary along the track as well. For example, a higher running speed for vehicles often equates to a tighter tolerance and hence a lower threshold before an issue becomes reported. Now we'll actually look at AssetWise Rail Condition Analytics. So Bentley has released a new cloud-hosted pre-configuration and packaging of its technology to the market to tackle all of the issues that we've just discussed, named AssetWise Rail Condition Analytics. To describe the capabilities and benefits of the solution, we need to cover the key areas of the required source data and the required analytics to turn that data into information. And we can then look at the visualization side of things as well. The concept of consolidating the data into a single source may seem simple at a high level. However, one reality is there's no international standard on the format of track-related linear data. Each source and/or each vendor of hardware generates the data in its own independent standard, its own independent format, and these can even change from year to year. The basic concept of rail condition analytics is to support decision making and applying the right work in the right place at the right time. With track maintenance, this requires consolidating data created when collecting the data. The methodology of consolidating data silos for track maintenance has 5 steps. Firstly is collection. This is done through inspections, by track recording surveys, but bringing together maintenance records, visual inspections, GIS data, ground penetrating radar, ultrasonic imagery, the list goes on of possible data sets that can be used. Historically, these data sets used to live in separate silos that were collected for a particular purpose, they were used for that purpose, and they remained in the silos. There was limited visibility of them. The data as it's collected, we have to keep a record of in its original form so that we've got an audit trail right the way back to what came from the recording vehicle. So everything that happens from that recording downstream, we need to have a full auditability associated with it. The first thing we need to do when we receive this data is a level of aggregation. So we clean and normalize the data and pull it together into a single system that allows us to reference between the data sets. All modifications of the original data are actually stored away in isolation, and then the cleaned data or the validated data can then be used for subsequent analysis and visualization. In the analysis phase, we can figure the analytics to pull out whatever information we want to from the underlying data that's actually been recorded. So we may use statistical analysis, for example, to look at the past, the present, and the future condition of the asset to be able to help us make more informed decisions. So finally, those informed decisions. What we're trying to do is turn the data that we have into actionable information that provides insight that in turn can drive optimal maintenance decisions. It's through optimization, rail and transit owner operators can improve the reliability of their networks, but most importantly, they'll improve safety within the organization and to the public in general. So let's have a look at the typical source data sets for rail condition analytics. Firstly, the track geometry and rail wear. These sit at the core of the solution, giving snapshots of the geometric and wear condition for the network each time a survey is undertaken. Different channels can be used for different purposes, which in turn drives both the analysis and visualization requirements to fully benefit from the data. For example, vertical and lateral geometry can tell us about the ballast condition and deterioration rates over time, whereas curvature, cant, and lateral wear can be used to identify areas where the rate of rail wear is excessive and support changes to extend the rail life. Maintenance and renewal records serve a number of purposes in linear decision support. They allow us to identify areas which are being more heavily maintained, to allow us to deep dive into problem areas and research why they are behaving as they are. They allow us to assess individual maintenance activities to ensure that they were both appropriate and effective, and support future decisions based on historic maintenance effectiveness. They also help with trending and prediction of future asset condition, as predictions need to be made aware of maintenance and renewals in order to better determine what might happen in the future. Finally, they can help us to see any unexpected effects from maintenance. Fixing one asset in a system may have an unexpected detrimental effect on other assets at the same or similar locations. And of course, we're not trying to maintain the assets in a fit for purpose state, we're trying to maintain the system in a fit for purpose state. Asset data is used for one of two reasons: either to help determine the root cause of an issue if the asset materially affects deterioration of linear assets, or to add context to data that is being visualized. The network definition is used to underpin the whole solution. It provides the linear referencing systems and track naming conventions for all of the imported data, as different asset disciplines may use different ways of describing location and different names for the same piece of track. As the system understands the entire network, it can also be used to report at a route level as well as a track level, as deterioration at the same location across multiple tracks can be an indicator of an underlying issue, especially when linked to the asset register. As well as a standard set of data sets we work with, we have a set of pre-configured analytics that can be easily tailored to meet the specific needs of each user. All of these are performed fully automatically against measurement data as it is imported. Firstly, there's data cleansing. As we're moving to a condition-based maintenance decisions, the data representing the condition becomes critical. This data often contains a number of issues such as location errors, low speed errors, gaps in the data, and so on. As part of the import process, these are detected automatically and, where possible, corrected automatically in the source data, leaving a copy of the as recorded so there's a full audit trail back to the original recording. Exceptions are then calculated based on rules supplied by the end user. These can take into account other attributes of the network, for example, gauge thresholds varying by degree of curvature. As the exceptions are calculated from validated data, the system can also reliably identify repeat faults, i.e. areas where faults of the same type have occurred at the same location within a defined timescale. The system also derives locations of clusters of similar faults, as these might be treated in a single maintenance activity or may trigger a deep dive into the root cause or a change in the maintenance strategy. Track quality indexes are measures of the condition of the entire network rather than just points where there's an issue. These can be derived from track geometry and rail wear to provide useful metrics to compare different parts of the network, and can also be used to determine the rate of deterioration of the asset over time and the effectiveness of maintenance and renewals. As well as being able to plot the historic rate of deterioration of the geometry or the rail, the system can also predict the future condition based on the current state and the rate of deterioration, and can identify areas that will require future interventions. This allows us to start moving from a reactive world into a proactive world of maintenance, as well as to understand where our problem areas are and exactly how effective maintenance has been in tackling both the current condition, the value of the track quality index, and the underlying issue, typically indicated by the rate of change of the track quality index. Finally, visualization is used to expose all of this data, the imported values, and the information, the derived values seen with context, seen in context with meaning attached, to support maintenance decisions. Due to the number of types of data, we tend to use a swim lane view by preference to visualize this data. Let's talk a little bit more about data quality, as this is so critical to the decision-making process. You cannot make informed decisions with poor data. If you receive poor data, make decisions based on that data, you will make poorer decisions for the organization. So understanding of data quality is essential to preventative maintenance. Firstly, we need to look at the accuracy of the data. For example, how well can its location be identified in the real world? An example being, if a broken rail is reported at kilometer 20 along a route, how close to kilometer 20 is the actual broken rail that we need to be able to treat? So how well do we relate to the real world? Next, we look at repeatability and reproducibility. So if the same item is measured several times by the same equipment for repeatability, how closely do the measurements match? Reproducibility is very similar, but if the same feature is recorded multiple times, how close together are they, especially if they're recorded by different systems? For example, if a broken rail is reported at kilometer post 30 in one recording, how close to kilometer post 30 is the same report in all of the other recordings that we have? For rail measurements, it's sometimes the case that the location accuracy is less important than the location reproducibility. This is because if we can get the maintenance crew close enough to be able to do the repair, that's what accuracy is giving to us. But in order to trend automatically over time, we need to have reproducible data. And we typically, for that automation to work, need a tighter tolerance on the permitted error that we're seeing. When data is trended to predict track failure, it's important to ensure that the trend observed is due to track deterioration or asset deterioration and not location errors or instrumentation issues. The track geometry data, because of this, has to be treated like any other asset. Indeed, it should actually go through the same asset management regime as the physical assets, because it's becoming more and more critical to the safe operation of the rail network. Finally, we come on to data visualization. The primary mechanism for visualization of imported and processed linear data is a swim lane diagram. This allows end users to view any combination of data in whatever style is most appropriate to the task at hand. Each swim lane can in turn be configured to show any combinations of data, allowing anything from simple summaries of track condition to complex root cause analysis to be pre-configured within the same system. The user can then zoom in and out to see an entire corridor, or in to look at just a few feet of track. So let's have a quick look at each of the types of view in turn. Firstly, what we call a layout view. This is a view that allows the end user to visualize a schematic representation of the track layout, complete with switches, crossings, and any required asset locations. Tracks can be selected to show the associated data in the remaining swim lanes, or deselected to allow route level information to be displayed. The x-axis represents distance along the track in this instance, and all of the other views share the same x-axis. A plot view. This allows the end user to visualize raw measurement data from a wide range of recording vehicles. The example here shows mean lateral alignment from track geometry. The y-axis in this instance represents the recorded value, and the x-axis is distance along the track. This view supports multiple runs over time in the same view, so that historic changes can be clearly shown. A range of highlight capabilities also exist. In the example shown, the blue highlights represent straights, transitions, and curved tracks, but we could equally be highlighting up locations of faults, locations of rapid deterioration, for example, or even asset locations or regions around asset locations. Finally, the date view. This allows the end user to visualize events that have occurred along the track, for example, maintenance or speed restriction. In this example, we're looking at changing track quality indexes. The y-axis represents time, with the oldest data at the bottom and the newest data at the top. As with all other views, the x-axis represents distance along the track. The colors show how the track condition has changed over time, with green being good track, yellow being satisfactory track, and red being bad track. And all of these are configurable parameters. In some areas, the tool has been able to work out that it can reliably predict the future deterioration of the quality index as well. Combining a view like this with the maintenance events, track faults, and inspections gives a holistic view of the current state of the asset, the changing condition over time, the maintenance and renewals undertaken historically, along with their effectiveness, and the potential future condition of the asset. This combination of data and information is the core view required to enable a transition towards condition-based maintenance and then on to proactive maintenance, and also to assess maintenance effectiveness to identify good practice and opportunities for improvement. So, in conclusion, the key benefits for the solution are: firstly, it helps us to understand track condition and deterioration to support better track maintenance and renewal decisions. Secondly, and critically, pre-configuration enables rapid implementation, which reduces costs and enables a more rapid return on investment. The system supports with knowing where and when to work, which in turn helps your engineers do the right work in the right place at the right time. And it can be used as an enabler to change processes to improve efficiency and safety. The key benefits, as I stated at the very outset, are actually achieved by working differently, not just by trying to do what we currently do faster or more efficiently. We need to change the way that we work, change the processes. This is simply a tool that facilitates that change. Our linear decision support software has been continuously evolving over the last 25 years now, and is now being implemented or in use at a wide range of owner operators, both in the US and elsewhere around the world. Many of these users are using multiple data sets to support the definition, prioritization, and validation of maintenance and renewal plans for linear assets. Some of the more advanced are moving into predictive or deterioration modeling, which is also covered in the solution. And some are working on linear maintenance and renewal planning, so possession optimization. That's everything I was going to cover in my presentation today. So thank you very much for your attention. Please find my contact details on the final slide if you have any specific questions for me in the future. But for now, I'll open the floor to any questions that you may have.